Let's take a look at Fathom to do some hypothesis testing and confidence intervals for working with one mean. Here, I've used the import U.S. Census data feature of Fathom to create a collection of 100 observations from the 2000 census, and here we have just Pennsylvania residents, and we have their age, gender, and marital status. I'm going to start by renaming the collection PA 2000, and we're just going to do a hypothesis test with age and a confidence interval with age. So before I look at the distribution of ages in a graph, let's say that maybe the mean age of Pennsylvania residents in the past has been 40 years old, and I want to see if it's significantly different than 40. So I might start by looking at a graph first, just to see where I think the mean might lie. It's possibly close to 40. That's a dot plot, and here is a histogram. So using this set of 100 observations, I'm going to do a hypothesis test for the mean, and I'll drag the age attribute here, and I want to see if the age has changed. If I suspect that the old age was 40, and I just want to see if it's actually, let's say changed, then we'd have not equal to. If I suspected that the mean age has gone up, actually let's test to see if the mean age has gone up. I mean, the population is getting older. Healthcare is making people live longer. So let's see if the mean is significantly greater now than 40, and we run our hypothesis test here, and notice we have a test statistic, a student t-value of negative 0.72. Notice there's 99 degrees of freedom. That's because our sample size was 100, and our degrees of freedom is one less than our sample size. And notice here it gives us the wording of our conclusion, or at least tells us what our p-value means. If it were true that the population mean of age were equal to 40, then the sampling process were performed repeatedly, the probability of getting a value for students t this great or greater would be 0.76. In other words, it looks like actually that the mean age is actually less than 40. We can actually change this to not be verbose, and this just gives us the raw numbers like our calculator does. Notice it also gives us our null and alternate hypothesis. Also, we can show our test statistic distribution with the shading, showing this would be no change compared to a mean of 40 or a z-score of 0 if there's no change at all. If the test statistic value, if the mean was exactly 40, this is where we'd be. But our test statistic value is negative 0.72, which puts us below the mean. 0.72 standard deviations below the mean, so we fail to reject the null hypothesis. We can also create a confidence interval, so let's do that by choosing estimate. If I want to get an estimate of the mean age, and so I'll drag age over here, and this produces a 95% confidence interval. Notice that once again we can change that from verbose to not verbose, remove the extra words, and we have our count 100 in our sample, our mean, our standard deviation, our standard error. This is basically the standard deviation. Notice the relationship here. If we were to take the standard deviation and divide by the square root of the sample size, which in this case would be dividing by 10, we would have our standard error, and then we have a 95% confidence interval. Notice you can actually change this to a 90% confidence interval or a 99% confidence interval, and the numbers change automatically. So let me go back here to change this to be verbose again. Notice it tells us the meaning of the 99% confidence, saying if this sampling process were performed repeatedly, the confidence intervals generated would capture the population mean 99% of the time. You are going to now be doing a problem similar to this, where we're going to take a look at the mean power production of my solar panels.